Hello everyone. Welcome back to the third session of ETAP. Uh, I'm sharing my screen. Can anyone confirm whether my screen is visible to you?
Visible, sir.
Yeah, okay, good. So welcome back to our third session. Can anyone tried with the option what we have seen in the last session? Yeah, okay, good. So I will recap that once again. So after opening the software, first we have to do some initial setting. So the first one is the information. So in the information, some basic details about the project we need to enter. So this one is optional. Then second one is the standard. So we have to set the standard. So based on the country, whether it is IEC or ANSI. So now I am setting with I So now I will set with IEC standard and 50 Hz frequency, and I will change the unit system to metric. So I told you know. So IEC standard is IEC, frequency is 50 Hz, unit system is metric. So English for ANSI and metric for IEC. Then date format month to date month year, then after that okay. So this setting has been done. Then third one is auto save option. So if you want to enable the auto save option, you just press the auto save and you just enter how many seconds you want to save. 5 minutes means, so every 5 minutes it will save the data. Okay, good. Then suppose if you are include this page is project edit space. So in that right side, the first set of column is the AC component. In the second row, the first one is instrumentation elements. Then in the second row, the second one is that DC elements. So we have to just pick and uh, paste inside the working space. Suppose if we want to copy the bus means what we need to do, we need to just press the element here and we need to just paste it in inside the working box. Suppose if we deleted any element in this working uh, space, then it will go to the system dumpster. So distance dumpster is here. So all the selected element will be appear here. So here I deleted two elements, that is bus 1 and 2. So for that reason, the next bus what I have selected, it is automatically renaming as 3 and 4. Suppose if I need to change this bus number to 2 means, so system will not allow because that id is already exist. So in order to continue the id continuously, so we have to delete the element in the dumpster. So with that, now we can able to change it to bus number 1, and this could be bus number 2. So in the bus, first what we have to do, first we have to enter the bus ID, then bus voltage. So just I'm considering 33 kV, then this bus can be 11 kV. So one typical one. Then I'm just connecting to winding transformer. For connecting any element, so if you move the cursor to the equipment, then the connection point will be turned into pink color. So that is the identification. So if you click it and if you're trying to move towards the bus bin, that bus also will the color change to pink. So if you drop it there, then it will connect automatically. It is simple connection. That is the one way. So power grid. So in the other way, how we can connect? So we have to open the element and the bus will be there. So if you need to select the bus ID, then it will connect automatically. That is the another way. So two way we can connect it. So for the load flow analysis, so uh, only rated kV is sufficient. So that is taken from the bus voltage. So transformer we need the ID, then connected bus. So it is the HV winding is connected to primary, then secondary winding is connected to bus 2 3311. So here voltage will be there. So this will be easily we can able to track it. Then we have to go to the rating page. So in the rating page, we have to enter the voltage rating that will be automatically updated. Then second one is the power rating. If you power rating in MVA, here it is in MVA. So here by clicking this MVA, we can change the unit. So now it is VA, now it is KVA, now it is MVA. So based on the transformer rating, we have to update it. So and also we have seen that some location we have to derate the rating of the transformer. The derating is available here. So if you don't want to derate it, then we can put it user define and we can put it enter 100%, 10 percentage. That's all. If you want derated, then we can derate it. If not required, then we can just ignore it. That's all. Okay. And in the impedance page we have two impedance, the positive sequence and zero sequence. So we have to enter the percentage impedance and for a positive sequence and negative sequence. This will be based on the transformer manufacturer data. So some typical values are available in ETAP library that we can use it for time being for learning purpose. So by clicking typical Z and XBR, it will update the typical impedance value based on the voltage rating and power rating. So and also we have seen that jet variation, that is transformer impedance variation for the OLTP operation. So so in the positive tab and negative tab, if we the nominal rating what the impedance the 8.35 is given here, it's only for the nominal voltage. So now sorry, nominal tab. So whenever the OLTC, the tape changing is operated from the nominal tab, so the impedance will get varied. So in order to capture the impedance, so we have to update the impedance for the negative tab. So this one will be -5 negative tab, this one will be +5 negative tab. That we need to add it here. And one more thing is that the load flow analysis in the last session I opened the IEEE standard 399, IEEE 3 399. So in this standard, some the theoretical information about the power system analysis available. So I suggested everyone to just to go through the load flow analysis details. So the basic information is available here. Then how we can consider the system input data, how to solve it. So input data for generator, bus, branch, transformer, all the data is available. So I told just to go through the basics of it. So this can be available in this one. So it is freely available, so you can just to go through it. Then the impedance tolerance. So in order to find out the worst scenario, normally what we will do in the load flow analysis, we will consider the tolerance in it. So in a transformer, the transformer manufacturer will give the impedance with some tolerance in percentage. So that could be somewhere around uh, up to, it can go to 10 to 15 percentage tolerance in impedance, that is based on the power rating. So the impedance variation is given in IEC standard, I think 60076. 60076. In that standard, the impedance variation for the different power rating transformer is available. So based on that, they will give. So that impedance variation, if we need to capture, so what we will do in the general practice, in order to get the worst scenario, we will consider the positive tolerance for the load flow analysis and negative tolerance for the short circuit analysis. So it means in the load flow analysis, we will consider the positive tolerance. So it means, for let's say, suppose if it is 10 percentage positive tolerance, means in the nominal of 8.35 percentage of the tap. So what we need to, how we have consider 8.35 percentage multiplied by 1.1, that is 10 percentage. So the new transformer impedance will be 9.185. So what how we have to do, how we have considered 9.185 impedance for the load flow analysis. So when we are doing the short circuit analysis, that time we will consider the minus 10 percentage. So 8.35 multiplied by zero point 0.9, so it will be 7.1 7.5 percentage impedance. So here it will be 7.15 percentage. So what this ETAP software will do, so based on the impedance entered here, so it will consider the analysis based on this one. So whenever the transformer is operating in the tap, that is OLTC is operated, that time it will calculate this will consider this impedance also along with the impedance what we have considered for the jet variation to calculate the load flow scenario, so that we can get the worst case. So it is some basic information. So in load flow, we will consider the positive tolerance in transformer impedance in order to get the worst case scenario. Similarly, in short circuit study, we will consider the negative tolerance, so that we can get the worst case scenario in short circuit study. Please note this point. This will be a typical interview questions. So you please note the note this point. So how to consider the impedance tolerance for the power system analysis. So this is the one of the interview typical interview point. Then next one is the transformer tab. I told at this time being, we can consider this tape changer in a later one. Then about the grounding page, in grounding page, first we have to do, we have to select the transformer vector group. So here it is primary. In the primary winding it is delta. In the secondary winding it is star. So if we need to change it, then we can change it. So by clicking, we can able to change. Now it is delta in primary, star in secondary. So that's all the data we need to enter for the short circuit, sorry, load flow analysis. So I told in the last session, for carry out any power system analysis, we need minimum two buses. The first two is the swing bus and second one is the load bus. So we need minimum two bus to two bus we need to carry out the power system analysis. So as we know, we have three buses: swing bus, generator bus, and load bus. For any analysis after any power system analysis through software, we need two bus minimum. One is the swing bus, second one is the load bus. Okay, suppose if we consider the practical system, in a practical system there will be no swing bus. So in that case, you may think then how we are considering the swing bus in a practical system. So in a practical system, there is no swing bus. The largest capacity generator generally considered as a swing bus in the analysis. Suppose if there is no power grid is available, only generators alone is there means. So how we consider, suppose if 10 generators are there in a system, so in among the 10 generator, the higher capacity generator, for an example, the generator one is 200 megawatt, remaining 9 generators are 100 megawatt means we will consider 200 higher capacity generator. The 200 is the higher capacity generator. That generator we will consider as a swing bus and we will execute the analysis in that configuration. So now we have two buses, so swing bus and load bus. So for time being, I just connected this static load of 4 MVA, static load of 4 MVA at 100 percentage power factor in static load. So we have to enter the power rating in MVA and power factor. So power factor we normally will use per unit value, but in ETAP we have to enter in percentage. So the value, what are the value we need to enter in percentage. So there they mentioned the percentage symbol so that you can easily understand it. So it is at unity per factor. So once now I have done the simple two bus system with one power grid and one static load of 4 MVA. So once the modeling is done, then next we have to go to the load flow option in the right. So once you entered in that load flow option, so first we have to set the edit study case. So the suitcase symbol is edit study case. So we have to go there and you have to change this case ID. So I'm setting study case 1. So I'm just I'm just changing the IDS study case 1. So it means it will save all the analysis in this name study case 1. Then next what we need to do, we need to select the method. So here three method is available: adaptive Newton Raphson and fast decoupled. So we have to select one. So normally we will use Newton Raphson method and iteration. So the default is 99 and the precision is 0.0001. So then click OK. Then in the right side PV, if you move the cursor on top of it, you can able to see the explanation run load flow. So it means by clicking this, we are just running the load flow. So now the load flow is executed. So for that, what we have to do first, we have to go to the display option. In the display option, we have to enable the show unit and the power flow rating. So presently it is in kVA, so we need to change it to MVA so that we can see the values in terms of megawatt range. So in that I just selected megawatt and megawatt so that I can able to see how much megawatt and megawatt is flowing through the line. Then in voltage, so we have k voltage in kV, voltage in percentage, voltage in volt V. So I am just selecting kV. So after now clicking that, uh, so it's the load flow result. So in the load flow result, mm, in the load flow result, the 4 MVA static load is consuming almost 3.97 megawatt and the reactive power requirement is 0. So it means it is operating at unity power factor. The voltage at the receiving end bus, that is bus number 2, is 10.96 kV. So and in the transformer, as we said, in the primary side, the real power is 3.98 megawatt and the reactive power is 0.142 mbar. So you may think that the load connected in the transformer secondary is unity load. So it will operate only on the unity power factor. So it is taking in the LV side, it is not taking any reactive power. Then you may be surprised that in why in the transformer HV side it is drawing some reactive power, that is 0.142 megawatt or 142 kVAR. So you may be surprised that the reason is that the transformer impedance. So we know transformer is a inductive based device. So it has the impedance. So in the transformer impedance, it not only having the resistive component, but it also having some reactive component. So due to that, the transformer always needs some reactive power to energize, not only the energize the transformer. For operating the transformer we need some reactive power. So that reactive power it is consuming from the power grid. So and also you may see that here the power flow, the active power is consumed by the transformer is 3.98 megawatt, but here it is 3.97 megawatt. Then what is the why there is a small difference in 0.01 megawatt? So 3.98 minus 3.97. So it is 0.01 megawatt or 10 kilowatt. Okay, so why that is the difference? The difference is the power loss. So in as we know, the every equipment having some power loss, no, due to the internal impedance. So that is the loss due to the resistance components in the transformer. So 10 kilowatt is the overall losses in this transformer. So this 33 kV is the primary bus voltage. I hope now everyone is understand the simple two bus system. Okay. So now what I'm going to do, so I'm going to change the load, that is the static load of 4 MVA into 6 MVA. So you please note that when the load is 4 MVA, the secondary bus voltage is 10.96 kV. So now I changed into 6 MVA, 6 megawatt. Okay. Now you can able to see the bus voltage is 10.96 kV. This is not 10.96 kV. It is 10.94 kV. So it is drawing 5.93 megawatt. So it is drawing little higher power from the grid because of the losses in the transformer. Okay. Suppose if I need to change the power factor. So now it is operated, the static load is operating at unity power factor. Let's say I am changing the power factor into 85 percentage. It means the static load rating of 6 MVA is operating at 85 percentage power factor. So that time it will maximum draw 5.1 megawatt of real power. You just see it is drawing 4.78 megawatt of real power at 2.96 mbar of reactive power. You know something, here you can able to see the load rating is 5.1 megawatt and the reactive power is 3.16 mvar, but it is not taking the rated value. Here it should be 5.1 megawatt, and this one should be 3.16 megawatt, but it is not taking because the bus voltage is reduced. It is no longer the nominal voltage of 11 kV. The bus voltage is reduced to 10.65 kV. So that is the reason it is not able to draw the rated power. Okay, suppose.
Shiva, Kiran has some query. The hand raise is there. Yeah.
Yeah, yeah, Kiran, yeah, you just unmute it and you can just ask.
My doubt was, no, previous case when the load was unity power factor,
Hmm.
uh, the load is around 4 megawatt and it is not drawing the full no capacity.
Hmm.
So, is that 11 kV that bus 2 is operating? I just not observe the previous one.
The reason is the voltage is not a rated one.
Oh, okay,
So
that's fine, sir. That's fine.
the operating voltage is not the rated one. The moment operating voltage is reduced from the nominal voltage, then the variation you can able to see.
Yeah, yes, sir. Thank you,
So
sir. Thank you for the
yeah, okay,
clarification.
good.
Thank you, sir.
Okay, so so in order to normally what we will do in order to improve the voltage, so first option what we will do, first we will use the OLTC, that is a tape changer available in the transformer, so that we can able to maintain the voltage to 11 kV. You just see here, without any transformer tap changer operation, the bus voltage is 10.65 kV. So in order to improve this 10.65 kV to the rated voltage of 11 kV, so we have to operate the transformer in the ETAP. So we have both the OLTC operation in tap page. The fixed tap is the off circuit tap changer, and the LTC load tap changer is the on load tap changer. So first we will try with the off load tap changer. So we have two options. We can have the OLTC in primary winding or secondary winding. So normally the OLTC will be available in the primary winding, so that it can able to control the voltage in the secondary winding. So now I am just changing the tap in the primary winding to minus 2.5 percentage tap. So the moment I changed the transformer tap from nominal tap 0 to minus 2.5 percentage tap, so the voltage is little bit improved from 10.64 to 10.92. Suppose if I change one more position, that is minus 2.5 to minus 5, then again the 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 LV bus voltage get be increased. So now it is 11.21 uh, kV. Okay, no? So like that we can operate the OLT off circuit tape changer in this tap position. So in a practical transformer, mostly in the distribution transformer having off circuit tap changer, but all other the power transformer in the substation or in a generating plant, those transformer mostly having the OLTC, load tape changer. Okay, so based on the tap changer available in the particular transformer at the particular project, we have to consider this tap changing operation. So transformer tap changing operation is the first step to maintain the voltage profile in the low voltage bus. So in this 2 bus system, the bus 2 is the low voltage bus. In order to improve the voltage in the bus 2, we have to adjust the transformer tab to improve the bus voltage. That is the first option. So now I moved back this transformer tab position to 0. Now it will the voltage will go to the original value 10.65. So now I will explain you how to model the on-load tap changer. In a fixed off-load tap changer, there is no modeling. Just we can vary the tab just clicking this arrow mark. So our on-load tap changer is not like that. So for that we have to model it. So first one where we have to keep where the OLTC is available, that is in primary, we have to just click it. Then here in this you just press the LTC, that is load tap changer. So in that first we have to selected the regulated bus. Regulated bus means in which bus voltage we are regulating. This is just a 2 bus system. Suppose if 10 bus or 20 bus is there, so which bus we are considering as a regulating bus, or which bus we have to maintain the bus voltage. So that bus we have to select. In this one it is bus 2, so we have to select the regulated bus, that is bus 2. Then voltage control, the voltage is 100 percentage, and here you can able to see the upper band and lower band. So the upper band and lower band is what it means, the percentage change of tap. For an example, we have 10 tap, so the 0th tap is the nominal tap. Okay, suppose if I am changing the tap from nominal tap to tap position 1 means, so how much percentage it will change, that percentage is this one, 0.625. Okay, so the upper band means in the positive direction 0.625, variation in one tap will increase the tap position in 0.625. Similarly in the lower band it is the negative side 0.625. Then the tap number of tap, so here the minimum number of tap is 10 and maximum number of tap is 10, so totally 21 taps will be there. So how it means, in the minimum tap we have 10 numbers, in the maximum tap we have 10 numbers, and also we have one more tap, that is the nominal tap. So by considering the nominal tap, so we have 21 tap in the transformer. Okay, so when the minimum tap is operated to tap position 10, that time the voltage is in the 33 kV side, it can be 29.7 kV. In the maximum side it is 36.3 kV. So step size is available here. So this is the step size 0.625. So this is one the typical value. Suppose if you want to increase the tap based on the requirement, you can just adjust it. Suppose if you want to 1% tap mean, you just put 1% tap here. So accordingly you just update this upper band and lower band. So time being I am considering 0.625. Okay, then here two more option will be there, initial and operating time delay. So what it means, in a practical tap changer, let's say the tap position is nominal, and if you want to change the tap from nominal tap to positive position 5 means, it will not instantly change all the tap 1 2 3 4 5. It will not do like that. So what the OLTC will do, first it will change the tap from nominal tap to tap positive tap position 1. Then it will wait for some seconds. Then after that it will change the tap position from 1 to 2. It will wait for some second. Then 2 to 3, 3 to 4, 4 to 5. So that time is called, here it is time delay. That delay we need to enter it here. So that value will come here. Okay, so I'm not just considering any value here. So it means it will instantly operate from all the tabs. So like this we have to operate. So here we enabled the AVR, that is the automatic voltage regulator. Then we just model the tab changer. So here one more option is there, that is operating tab. Presently which tab the transformer is in now. So 0 means nominal tab. Suppose if you want to change the tab, if it is operating in different tab means that one we can change. So as I told, 0.65 is the tab position for one change. So just I am clicking the positive upper arrow. So it means I changed the transformer tab nominal position to first position. So that tab is 0.625. Okay, so like that we have to do it. So I just changed it. Okay, I just changed the tab position. uh, After that it start running the simulation, and it can able to maintain the bus voltage as 11 kV. Okay, suppose if I disable the automatic voltage regulator function in function, that is OLTC function, in that case it will not maintain the voltage. So now I just disable that OLTC function. You just see the voltage went back to the original voltage 10.65. Okay, so by enabling this tab changing function, it will maintain the bus voltage. So this is the first option, uh, changing the transformer voltage. So I will just go here. So if you just study this document first before when you are doing the analysis in the software, I'm just suggesting you to parallelly read this document also. You just parallelly read this document, and you have to verify it. So here the sum of the objective of the load flow analysis is transformer tab setting. So what we have done, the small variation in the transformer and seen, no, so that will comes under this. So finally what we will do, no, after the completion of the load flow, we when we are trying to give the report, no, that time we will suggest what we will suggest, the selected transformer tab, that is -10 to +10 with step of 0.625 percentage is suitable for the particular site. So that is the recommendation we will give. Suppose if we are not able to maintain the LV bus voltage as 11 kV with this plus or minus 10 tab means, we will increase it to 12 or 13 or 14 or 15. Okay, so that tab position we have to give. Okay, so that is the one of the objective of the load flow analysis. Objective of the load flow analysis, the transformer tab setting. Okay, no. So we have seen a real and reactive power flow. So in a branch we are seeing the real power flow and reactive power flow. No, that also is one of the objective of the load flow analysis. The steady state bus voltage. Steady state bus voltage means this is the bus voltage. In the bus 1 it is 33 kV. In bus 2 it is 11 kV. These are all the steady state bus voltage. As in the first session I told you, so the steady state bus voltage having the tolerance operating tolerance on it, so that depends on the country to country. Generally it will be plus or minus 10 percentage. In some country they will in some country they have the different requirement. For an example, I remember in Bangladesh the negative in the lower side it is plus minus 15 percentage. In the positive side it is plus 10 percentage. It is not plus or minus 10 percentage. In the lower side it is minus 15 percentage. In the positive side it is 10 percentage. So that is the requirement for the Bangladesh. And I remember the Ireland, the country Ireland. In the Ireland I think in the negatives in the lower voltage side it is minus 80 15 percentage. In the positive side it is not 10 percentage or not 15 percentage. It is I think in between value. So 12 point something will be there. That is the one. And in Egypt I seen that in Egypt it is plus or minus 15 percentage. So in the both in the lower voltage side and the higher voltage side it is 15 percentage. It is not plus or minus 10 percentage, it is plus or minus 15 percentage. So based on the country grid code, so we have to ensure that during all the load flow cases in all the buses the bus voltage has to be maintained. Since it is a simple two bus system, so we can able to maintain the voltage. Here it is 11 kV. Suppose if we have n number of buses, means we have to see all the bus voltage. Okay, the nth bus also the voltage should be within the tolerance limit. For an example, if it is plus or minus 10 percentage, the nth bus also the voltage should be plus or minus 10 percentage. So for an example, if it is 11 kV means in the negative side it will be uh, 9.9. In the positive side it will be 12.1. So in that operating range the voltage should be there. Okay, so that is the one method. Then the second one is that uh, using the reactive power compensation. I just disabled that AVR function. So now the bus voltage is 10.65 kV. So as we know, uh, in order to improve the voltage we can use the reactive power source, that is capacitor bank. The general relation is that voltage and reactive power is directly proportional. Similarly, real power and frequency is directly proportional. So in order to improve the voltage from 10.65 kV to 11 kV, we have to use the capacitor bank to supply the reactive power so that the voltage can be improved. Suppose if I need to reduce the voltage further down, now it is 10.65 kV. Suppose I need to reduce the voltage to 10 kV, means what I have to do? I have to consume the reactive power so that the voltage will get reduced. So for that what I have to do? I have to use the reactor to consume the reactive power so that the voltage can be reduced. So I will just connect one capacitor bank in parallel to the load. So for the capacitor bank, again we need to enter the ID and the connected bus, then rating, voltage rating, then MVR rating. So how many MVR per bank? So here the number of bank is there. So it is just we can use any number of bank. So for easy understanding, I consider just only one bank, and its rating is 2 MVAR. Okay. So what it will do when the MVR, the capacitor bank is connected to the line, it will consume, it will supply the reactive power so that the voltage can be improved. So can you able to see this one? The capacitor bank, the 2 MVAR of capacitor bank is supplying 1.94 MVAR of reactive power, so that the bus voltage is improved. Earlier it was 10.65, now it is 10.84. Okay, how it is improved? Because the reactive power from the capacitor bank is used to improve the voltage profile here. Just here I forgot to tell you that the service connection, here service connection in and out. So in means the equipment is in service, out means equipment become out of service. If you just to put this service condition out, so it means the particular equipment will not be uh, used in the analysis. So here one option is there, that is called check circuit continuity. If we click that element, then we can able to see the element which is not in service, that will be in a different color. If you just press that, that is if you released it, now we cannot able to see that difference. If you press that, then we can able to see all the elements which is there in out of service, we can able to see that. Okay, so you just see that the load the load require drawing 2.96 MVAR of reactive power from the supply. So that supply is coming from the source, that is the power grid. If you see the power factor will be here. So if you put it in app and click the power factor at the source, that is power grid, is 82.71 percentage. Okay. So now I will just switch on the capacitor bank and see the thing. Can able to see the voltage at the low voltage side, the bus voltage is improved, that is 10.84 kV, and the load is still operating at 85 percentage of power factor. So we model the load as 85 percentage of power factor, so it is drawing the 85 percentage of power factor. In that 2 m bar, closer to 2 m bar, reactive power is supplied locally by the capacitor bank, so that the operating power factor is improved at the source point. Earlier it is 82 percentage, now it is increased to 96.4 percentage. So this one is called as reactive power compensation. So reactive power compensation means using the capacitor bank or any other reactive power source closer to the load, and supplying the reactive power to the load, so that the power factor will be improved. So that is generally the reactive power compensation. So we have used the 2 m bar of capacitor bank at the low voltage side bus 2. Suppose if you need to maintain the unity power factor here, so power factor equal to 100 means, then what we need to do, we need to again increase the power rating of the capacitor bank. Just I changed it to 3 bar capacitor bank rating. The power factor is improved to 99.71 percentage. Okay. So for to bring it to unity, then what we need to do? We need to again increase the reactive power. So now you can able to see the reactive power minus symbol. What it means, the capacitor bank supplying the reactive power, that is 3.5 megawatt, but the load needs only uh, 3.16 mvar, 3.16 mvar. So the remaining some reactive power will flow back to the grid. So that time the power factor rating will change. Earlier it is lagging power factor, so positive symbol generally we will consider as a lagging power factor. Earlier it is 99.97 lagging power factor. Now it is leading power factor, so some amount of reactive power is flowing back to the grid. So in order to avoid that, we have to limit the reactive power supplying by the capacitor bank. Okay, so now it is 99.98 percentage in positive, so it means lagging power factor. So it means the capacity, the reactive power is not flowing back to the grid. Okay, so now we are doing some optimization, no? That is called as reactive power compensation and optimization. Okay, so now we have seen the reactive power compensation through the capacitor bank at the low voltage bus, at the bus 2. Okay, so what will happen if I connect the capacitor bank in the high voltage bus? Just I am connecting the capacitor bank at the high voltage bus. So earlier I considered a 3.3 mbar of capacitor bank. The same rating I am just considering 3.3 mbar of capacitor bank, but the location is not at the low voltage 11 kV bus. It is 33 kV bus. 33 kV bus. Okay. So can you able to see the difference? Earlier the load alone is operating at 85 percentage of power factor, but the branch circuit, that is the transformer circuit, is operating somewhere around 99.9 percentage. But now can you able to see when the reactive power compensation device is moved from the low voltage bus to the high voltage bus, the load is operating at 85 percentage. The transformer, the circuit also operating at 85 percentage, but the power source remain is operating at unity power factor 100, but the internal circuits is operating at 85 percentage. This circuit as 85 percentage, at here it is 82 percentage. So what is the concern now? The concern is current. Okay, in terms of power loss. Okay, so as we know, the real power loss, normally how we will calculate it is I square R losses. So I square R is our real power losses. Okay, so whenever we connect the capacitor bank at the low voltage side, we are compensating the reactive power at this low voltage bus itself. So the current flowing through the transformer branch will not have any reactive component. so that it will give lesser power loss in the system. Now can you able to see the current flow in the low voltage side is 304.9 ampere when it is operating at 85 percentage power factor. Now I will just take the screenshot of this page. So what I will do, I will just put this low voltage capacitor bank in service, and I will make this high voltage circuit breaker out of service. Can you see the difference in the low voltage side? When we connected the 3 ampere of capacitor bank in the low voltage bus, so the load is remain 85 percentage, but the transformer circuit also 85 percentage. So it resulting to 304.9 ampere in the LV side, this ampere. But when we connected the capacitor bank in the low voltage side, the load is remain 85 percentage, but the transformer circuit is 266.9 ampere only. So there is a significant almost 40 ampere reduction is there in the transformer feeder. Okay, transformer feeder. So when we comparing the power loss, the 304 ampere current will increase the power loss. As we know, the power loss PL equal to I square R. Okay. In the case 1, the current is 304 square multiplied by R square. In the second case, it is 266 square multiplied by R. So R is in both the cases R is remain constant. That is the impedance in this line. Impedance in this line, the resistance alone will be giving the real power losses. That R alone is we have to consider that R is remain constant in the both cases, but the current is the difference. So absolutely 266 ampere will give the lesser power loss, and 304 ampere will give the higher power loss. Okay, so uh, the location of the capacitor bank for the reactive power compensation we have to do based on the optimization techniques. So optimization technique means in a large network where we have to connect the capacitor bank. So whether it is closer to the load or in between the bus or at the transformer LV bus, so by placing the capacitor bank where we can get the better results. That including better result means the first one is voltage. So in the all the bus voltage to be maintained. The second one is the reactive power Q, whether we can able to meet the reactive power or not. Then third one is the loss, P loss, P loss. So in which case the power loss is less. Okay. So generally the system will operate continuously throughout the year. Okay, so even a small amount of power loss occurring due to this will increase the energy loss in a significant way. So the power loss. So for an example, the power loss suppose happening at 100 watt. So 100 watt is 1 kilowatt. So oh, if the system is operating for 1 hour means, then it will be 1 kilowatt hour. 1 kilowatt hour per the power loss will be 1 kilowatt hour for 1 hour energy loss. So when the plant is operating for a 1 day, then power loss will be 24 kilowatt hour, that is 24 units. So if the plant, so for a case of 1 year, then 24 multiplied by 365. 24 multiplied by 365. So this much amount of energy will be lost in this low voltage network as a losses. 3760 units, or 8.7 megawatt hour. So that much amount of energy will be lost in this branch circuit due to the reactive power, inadequate reactive power compensation. So everyone clear as of now? If anyone have the doubt, please unmute it, and I will clarify it.
How is the grid model here?
I could not get you. Can you please repeat?
How is the grid modeled?
So the grid is modeled as a swing bus. It's a typical swing bus.
Okay,
So swing bus, as we know, so we know the voltage and the voltage angle of the swing bus, and real and reactive power is unknown. So
okay,
it will operate like that.
okay.
Okay, good. Any other questions? Yeah, okay, good. Uh, so I hope everyone is clear. So this is the typical one. This is the typical two bus system. So our practical system will not be a typical two bus system. It will have more number of buses and elements. I will just connect one power cable. So this element is power cable. Power cable is connected. So for modeling the power cable, we have to just open it. So for the power cable, first we have to, in the info page, we have to enter the ID and from and to buses. Then cable length. Let's consider 2 kilometer cable. So the unit is available here. Feet, mile, meter, kilometer. Just a 2 kilometer cable. Okay. Then number of conductors per phase, that is the number of runs per phase. So generally here it is, the typical value is 1. So you just can time for simple understanding, we'll just consider 1. Then again we have to go to the impedance page. So in the impedance page, we have to enter the positive sequence impedance and negative zero sequence impedance. So alternatively, how we can do, we can model the cable here through this library. So in this library, the ETAP have some predefined catalog, so that we can select it here. Can able to see the unit. It is English for the ANSI bin. then frequency 50 hertz, type AL means aluminum, CU means copper cable, then voltage rating, the number of conductor. So single core, two core, three core cables will be there. No, one means single core, three means three core. Then insulation we have studied PVC insulated cable, XLP insulated cable. So that will be available here in this one. Then source means based on what information they have modeled this cable. Then install, in the install mag is there, no? So mag means in a cable there is one element will be there, that is called armor. So armor means iron or aluminum or copper strip will be there above the cable to increase the mechanical strength of the cable. If it is there, then that cable is called as armored cable. So that armoring is mag here. If there is no armoring means it is a non-mag here. So for us, we are using we are using the metric standard. So I just selected a metric. Frequency is 50 hertz. Then we have what we have to do. We have to select which type of cable, whether it is aluminum or copper. I'm just selecting copper. Then voltage. So our voltage is 11 kV. I just selected 11 kV. So in here there are some predefined model is available. So we have to select one. Alternatively, we can use, suppose if any project specific information is available, those information also we can use it. So this is one some typical value. So I am just selecting this one. So here the cable size will be there. So the size depending on uh, the size depends on the current flow through it. So we have many number of cable sizes in millimeter square or square will be there. So in that we have to select one. So I'm just selecting 150 square. That's all. Suppose once you selected the library, then impedance page will be automatically updated at this point. Okay. So then I'm just trying to model an induction motor here. Induction motor. So induction motor, we have to enter the ID. Then single phase motor or three phase motor, that information we have to update. Then rating. So in the last session I told, if you press the HP, then it will change it to kilowatt, HP or kilowatt. So I'm just considering it is 1500 kilowatt motor. So this one will be PF means power factor. Here FL 175/50 is the power loading condition when the motor is operating at 100 percentage load. That time it will draw 92.66 percentage of power factor. So that information we have to update based on the manufacturer data sheet. Then EFF is efficiency in percentage. So here it is 93.94 percentage efficiency for 100 percentage loading, 75 percentage loading, and 50 percentage loading. So for the motor, so we have to update only in the info page and nameplate. So this much information only we need to update it. So after that, just to go to the load flow and run the load flow analysis. and run the load flow analysis. So earlier we have seen the bus voltage is closer to 11 here. So due to the increased load, so again the bus voltage is reduced. So now the transformer impedance is in off position. Okay. Suppose in order to improve this bus voltage to 11, what we can do, we can operate the transformer tap here, or we can increase the capacitor bank rating here, or we can add one more capacitor bank also in this low voltage bus, or in this bus 4, so that the voltage can be improved. So now I will just I will give one example with increased the rating of this one. So earlier it is 3.5 3.3, now I changed it to 4 MVAR. With the 4 MVAR the bus voltage is marginally increased. When I will change it to 5 MVAR. Okay, so with 5 MVAR of uh, reactive power, so the bus 2 voltage is 11.05 kV and bus 4 voltage is 10.99 kV. So the bus voltage is marginally improved. So now can able to see, so the power factor at the source is 99.29 percentage, but can able to see the negative sign. So it means the reactive power is flowing back to the grid. Okay. Okay, but one thing is that in this feeder, this motor feeder, the motor is drawing power factor at 92.66 percentage, so that this feeder having some higher power loss. So suppose if we connect one more capacitor bank closer to this motor, will supply the reactive power to this motor, so that the power factor of this feeder will be improved. So we can reduce some energy loss in this one. So in a plant, in a plant, we have to decide based on the techno-economical aspects. Techno-economical means the technical aspects based on the feasibility, where we can install the capacitor bank or bus 2 or bus 4 or bus 1. Technical feasibility. Second one is the economic feasibility. The economic feasibility economic feasibility is the cost of the installation. So due to the capacitor bank, then maintenance costs, etc., and also the return of investment. Sorry, corresponding to the energy loss. For an example, if I am installing the capacitor bank, then I am saving some amount of energy in the distribution feeder. So suppose if I am not installing the capacitor bank, the energy loss is high. If I am installing the capacitor bank, the energy loss is low. Okay. So at in if I am installing the capacitor bank now, then how much amount of energy I can save uh, throughout the year. So for an example, we have calculated somewhere around 8,700 unit per year, no? So okay, so for that unit we have some cost. Let's say 8,760 unit per year is the energy loss. Let's consider per unit cost is 5 rupees. So the energy loss due to the poor power factor is 43,800. Okay. Suppose in order to reduce the energy loss, what we need to do, we need to install the capacitor bank. That cost is somewhere around 1 lakh. 1 lakh. So how we will consider generally uh, the initial investment divided by operational saving, that is 43,800. So in a year of 2 years and 3 months, we can able to save the total installation cost. Suppose if I am spending 1 lakh rupees for the capacitor bank now, I will save the energy by means of it. By saving that amount of energy, will give the 1 lakh rupees saving in the electricity bill in 2 years, 3 months. So 2.28, round off, I consider 2.3. So 2.3 month I can able to save that amount, that much amount of cost in the electricity bill. So that is the economic factor. Suppose if this factor here it is 2.3. So everyone okay, if I am installing the capacitor bank, okay, so I can able to save the energy this much, so that resulting in this much amount of cost in the building. So I can able to get that in 2 years and 2 months. This could be fine. Let's install. Okay, that is one option. In some case, suppose if it is 12.3, let's say it is 2.3, let's consider 12.3 in place of 2.3, just to consider 12.3. So it means I will get the energy saving of equivalent to 1 lakh rupees in 12 year and 3 month. In that condition, some people, that is a plant owner, may interested to install the capacitor bank and save the energy, or they will take the decision that let's don't invest on capacitor bank to save some energy that will give the equivalent energy saving after 12 years. I don't want to take that now, let it run at lesser power factor. Some people will take that decision. So that decision is taken based on the techno economical analysis. Okay, so the simple calculation I made, no, that is called as a typical economic analysis. At what year I can able to save the energy equivalent to the capital investment. Okay, now, so this is the typical one. So now suppose if I am just switched off this capacitor bank also. Okay. Earlier the voltage 11.05 kV is changed to 10.57 kV. Okay. So in order to improve the voltage, what I am trying to do, I am going to enable the transformer OLTC. So what it will do, it will try to maintain the voltage closer to 11 kV, so it will improve the voltage. Okay, so the transformer will maintain the trying to maintain the voltage in this bus 2 only. You just see this bus 4. This bus 4 is 10.93 kV only. It is not closer to 11, but it is 10.93. Suppose if I need to regulate this bus voltage, what I have to do? I have to change the regulating bus. In the transformer low voltage bus, there is a regulating bus, no, I have to change it to bus number 4. Suppose if I change it to bus number 4, so in that case what it will do, this transformer will try to maintain this bus the bus number 4 voltage as 11 kV. Okay, so like that we have to model. So since it is a software, I simply just changed the regulating bus voltage from bus 2 to bus 4. Bus bus 2 to bus 4, I just changed it. But in a practical system, how it will do? So now what we will do, we will have one equipment called RTCC, remote terminal voltage control. RTC or some transformer voltage controller panel will be there. So for that panel, what it will do, it will monitor the bus voltage. Suppose if you want to regulate the bus voltage at bus number 2 means, so that particular RTCC will monitor the bus voltage, that is bus number 2 voltage. So based on the bus voltage, it will given the command to the OLTC, that is tap changer in the transformer, for the tap position change. So based on the command received from the RTCC, it will try to regulate the tap position, so that finally the bus voltage will be improved. Okay, suppose if we need to if we need to regulate the bus number 4 instead of bus number 2 means, what we need to do, instead of taking the reference bus voltage from bus number 2, we have to refer the bus number 4 voltage, we have to measure the bus number voltage. So the RTCC panel will measure the bus 4 voltage. So based on this bus voltage, it will give the feedback or a control signal to the OLTC. So normally what it will, how it will happen, there will be, in a plant there will be an electrical room. In the electrical room, nearby the transformer will be kept it here. Okay, so this will be our transformer LVHV, transformer LV, transformer HV. Suppose if it is the outdoor transformer, inside the electrical transformer there will be some high voltage breaker, there will be some low voltage breaker, and there will be some this will be, you just consider RTCC panel. So suppose the first one for the bus number 2, no, for the bus number 2. So this is our bus number 2, bus number 2. So this RTCC panel, what it will do, it will just measure the bus voltage, it will just measure the bus voltage, and it will give the control to the OLTC will be here. This will be our secondary winding, this will be our primary winding. In the primary winding, OLTC will be there. So it will give the RTCC will give the control to this tap changer which is there in this transformer. So it will change the tap, so that the LV bus voltage can be improved. Okay, this one I think everyone is clear. Suppose if I need to control the voltage at bus 4 means, the bus 4 will be not at this location, so it will be in this location. So here some cable is there for 2 kilometer, correct, no? This cable is around 2 kilometer length away, 2 kilometer length away. Okay, so in that case what we need to do, so in that case we have to measure the bus voltage of this is bus 4, no? So bus voltage we need to measure here. This will not this one, this line will not be there measuring the bus number 2. This measuring this bus number 4 will be there. Okay, so taking the input near the bus is very easy, but 2 kilometer length auxiliary cable we need to lay. So auxiliary cable 2 meter length we have to lay. So in that there is some technical challenges were there. So, in order to avoid those challenges, in most of the cases, normally we will consider the LV, the immediate transformer bus voltage will be taken and given to the RTCC that will control the transformer tap changer. So in some cases, some specific cases, if we need to regulate the bus other than the immediate transformer bus, that is bus number 2, here the other bus is bus number 4. If we need to change it, means again we have to monitor the voltage at the bus number 4 uh, through this RTCC panel, and we have to do some challenges involved. Some challenges is involved in this cable. We have to come overcome those challenges, especially due to the voltage drop. So whenever we have to lay the control cable from this bus number 4 to this RTCC panel, that will be 2 kilometer, no? So in the 2 kilometers, some voltage drop will be there. Since it is the AC cable, there will be some voltage drop. That voltage drop we have to overcome. So that is some challenge is there. So I presume everyone is clear at this moment. So I that's all from my end for today's session. So I'm requesting everyone to just to go through the IEEE standard 399 and go through the various option in this software, especially the what are the components I teach you as of now. You just go through those components, and you just to do some analysis from your end, and you just update me if you have any concern in between before the next meeting. So today is Saturday, so our next meeting will be on Tuesday, the same 8:30 p.m. Indian time. So if you have any doubt, let me know.
I have still not received the code for that demo code.
Okay, I think just a minute.